Hello students, let's learn flow of two immiscible fluids.
So flow of two immiscible fluids is a multiphase flow. So in multiphase flow, there are two types. First is disperse flow, where fluid is flowing in continuous manner, but material inside is dispersed. And second is separated flow. In separated flow, fluid is two types of fluid is flowing with an interface. Example, oil and water. Oil is flowing over water in between, forming an interface. So these are two flat plates on which oil and water is flowing, forming an interface and two layers. So we can encounter such situation with transportation of petroleum products and water in chemical industry. An analytical solution is derived for fully developed flow. We will be deriving a fully developed flow analytical equation for fully developed flow of two immiscible fluids between two flat plates when fluids is having arbitrary viscosity and flow rates. Let's consider two immiscible fluids flowing in a narrow slit between two horizontal plates. So this is plate 1 and this is plate 2. And two immiscible fluids, let's consider oil and water is flowing with the density rho 1 mu 1, density and viscosity rho 1 mu 1, density and viscosity rho 2 mu 2. Alright, now this flow of liquid is in horizontal z direction. So in z direction, velocity is vz, and for x and y direction, velocity vx and vy is equals to 0. Now let's consider this fluid. Oil is obviously less dense than water. So we got this relation rho 2 is less than rho 1, right? And this is the interface this is an interface in between two immiscible fluids. This flow is only due to pressure gradient. So let's consider here at z equals to 0 and here at z equals to L, pressure is P naught and here pressure is PL, which is equals to small pl plus rho gl P naught plus rho g naught. And this plate have length L and width W. Now this is an incompressible fluid. And the flow is laminar flow. Also, the flow is steady and unidirectional. It is in z direction only. Fluid considered is Newtonian fluid, and only pressure gradient occurs. So, if you see velocity distribution, it's considered in x direction and in z direction. Velocity distribution is like this. For oil, it's greater, and at wall, it's getting less due to maximum shear stress, right? So on the wall, shear stress is maximum, velocity is minimum, and this is tau xz. It's actually on x plane and in z direction. So here, so when you consider a small shell like this, so this is a small shell that is having with delta x, and it's at distance x. Here is the x plane, so this is the x at this is at x distance. Let's consider the thickness of this fluid is b. So somewhere at x minus b, we will get minimum shear stress, x upon b, sorry. We will get minimum shear stress, where we will find maximum velocity, Vmax. So this will be the plane of zero shear stress. Now let's see in when we do momentum balance for it. So, well, let's find out momentum flux. in x direction, in z direction on shell. So momentum flux in z direction is WL, width into length. This is width of the pipe, and then width of the plate and length of the plate. Into shear stress tau xz at x, at distance x, that is here, to distance x plus delta x. So this is the momentum flux in x direction, in z direction on x plane, on surface x. Now force acting on it, external force acting on fluid. So external force acting on fluid is equals to what is the reason of fluid that's flowing in z direction? It's only due to pressure gradient. Therefore P naught minus PL per unit length on the surface of this plate, that is width into length. So this is the force acting on fluid. So let's do the cell momentum balance to find velocity profile and shear stress distribution. Let's see the assumptions before we move forward. Let us consider two immiscible incompressible liquids that are flowing in z direction in a horizontal narrow slit of length L and W width. Fluid is more dense. Fluid 1 is more dense than fluid 2. Hence, less dense, less viscous fluids will be flowing over the more dense, more viscous fluid, considering water and oil. Now, steady state condition, laminar flow, incompressible fluid, therefore density and viscosity, it will be constant for fluid 1 and constant for fluid 2. That is rho 1 mu 1 will be constant and rho 2 mu 2 will be constant. But rho 1 is greater than rho 2 and mu 1 is greater than mu 2. Now unidirectional fluid will be only flowing in z direction. Therefore Vx and Vy is equals to 0. Newtonian fluid. Let us consider the shell at distance x for thickness delta x. No end effect. The disturbance of flow of liquid at edges are neglected. Therefore whatever fluid is entering will be moving out from the narrow slit. The fluids are flowing under pressure gradient only. This fluid flow is only due to pressure gradient, due to pressure change at z equals to 0 and z equals to L. There will be pressure P naught and PL. So now let's do the shell momentum balance. Applying momentum balance at shell, we obtain rate of molecular momentum in, that is tau xz at x, minus rate of molecular momentum out, tau xz at x plus delta x, into WL minus external force acting plus external force acting on fluid, that is P naught minus PL upon L, into WL delta X equals to 0. Now divide by WL into delta X, we get tau xz at X minus tau xz at X plus delta X upon X delta X plus P naught minus PL upon L. So taking limit delta X tends to 0, what we get? Tau xz equals to P naught minus PL upon L dy dx. Now take on integration, we get d tau xz equals to P naught minus PL upon L into dx. Integrating both sides, we get tau xz equals to P naught minus PL upon L into x plus C1. To find value of C1, we need to find out boundary conditions. So boundary conditions are, let's see the diagram here. At x equals to 0, what we get at x equals to 0? An interface. So at x equals to 0, tau xz is equals to tau xz. Tau xz1 is equals to tau xz2. Now this equation for fluid 1 will be tau xz1 equals to P naught minus PL upon L x plus C1 1. And for fluid 2, this become tau xz 2 equals to P naught minus PL upon L x plus C1 into 1, C1 raised to 1. Now this raised to 2 for fluid 2. Now this equals to this. When x equals to 0, here we find out tau xz1 equals to tau xz2, that is, for shear stress acting on fluid 1 is equals to shear stress acting on fluid 2, because it is an interface at x equals to 0. Therefore, what we get for all these equations, 1, 2, 3 and 4, we get C1 equals to C1 for fluid 1 and 2 equals to C1. By Newton's law of viscosity, what we have, tau xz1 equals to minus mu1 dv1 upon dx, and tau xz2 equals to minus mu2 dvz2 upon dx. Now substituting this in equation 3 and 4, we get minus mu 1 dvz1 upon dx equals to p naught minus pl upon L into x plus C1 minus mu 2 dvz2 upon dx equals to p naught minus pl upon L into x plus C2 x plus C1 2 1. Now integrating both equations, so on integration, what do we get? dvz equals to minus p naught minus pl upon mu l x minus c1 upon mu 1. So this is same, so let's write C1 by boundary condition. C1 equals to C1 1 into C1 2, right? Now Vz1 equals to minus p naught minus pl upon mu 1 L into x square upon 2 minus C1 mu 1 x plus C2, and Vz2 equals to minus p naught minus pl upon mu 2 L x2 upon 2 minus C1 upon mu 2 x plus C2 2. Now to find this value of C2, we will see second boundary condition. So at x equals to 0, we see tau xz1 equals to tau xz2. Similarly, vz1 is equals to vz2 because velocity component is same at interface, right? The velocity component at interface will be same. That's why interface is forming at separation, and no gap only possible when velocity component is same. Therefore, by this boundary condition, C2 dash is equals to C21 is equals to C22 is equals to C2. Now at third boundary condition, at x equals to minus or plus b, so plus minus b, I have vz1 is equals to vz2 is equals to 0. So at boundaries, velocity distribution on the wall, on wall velocity is 0, right? Velocity of fluid 1 is equals to 0 and velocity of fluid 2 is also equals to 0 at wall. This condition at wall. Therefore, minus p naught minus pl upon 2 mu L B2 plus C1B upon mu1 plus C2 equals to 0. Similarly, for fluid 2, this is for F1, for F2, minus P naught minus PL upon L into B plus C2B upon mu2 plus C2 equals to 0. Now by subtracting equation A and B, we get value of C1 and C2. Subtracting equation A minus B, we get value of C1 and C2. And substituting this equation, this value of C1 and C2 in equation velocity profile equation, we get velocity distribution for fluid 1 this is my velocity profile equation for fluid 1. For fluid 2, for oil example, Vz2 equals to minus P naught minus PL upon 2 mu L x square upon 2 minus B value of C1 2 mu 2 L into mu1 minus mu2 upon mu1 plus mu2 into x plus P naught minus PL upon mu1 plus mu2 into P square upon L. So this is C1 and C2. Now Vz2 becomes minus P naught minus PL upon 2 mu 2L into B square common निकाला, then x square upon B square plus x upon B into mu1 minus mu2 upon mu1 plus mu2 plus 2 mu2 upon mu1 plus mu2. So this is velocity profile for fluid 2, right? Now shear stress, to find shear stress we need to put value of C1 and C2 there too. So shear stress becomes P naught minus PL upon L into x plus minus B into P naught minus PL upon twice L into mu1 minus mu2 upon mu1 plus mu2. So substituting value of C1, what I get, P naught minus PL upon L into x into B common x upon B minus 1 upon 2 mu1 minus mu2 upon mu1 plus mu2. So this is shear stress acting on fluid. So putting at x equals to 0, if we put at x equals to 0, so value of x, this becomes 0, then what I get, now xz equals to half of tau xz equals to 0. So if these these two terms become 0, x upon b is equals to half of mu1 minus mu2 upon mu1 plus mu2. So at x equals to 0, tau xz equals to 0. Therefore x upon b becomes half of. So this is the plane of zero shear stress. Plane of zero shear stress. Which lies somewhere here in the diagram of shell